You're listening to the Australian Water Association podcast series.
I'm Ellen Fanning. I'm speaking today with Dr. Ji Lu, a recent PhD graduate from the University of Queensland with a multidisciplined research background in the fields of nanotechnology, microbiology and environmental engineering. His paper is entitled Triclosan Spreads Antibiotic Resistance via Mutation and Horizontal Gene Transfer. Ji, lovely to be speaking to you today.
Hi, Ellen. It's my pleasure to have the opportunity to talk to you.
Tell me about antibiotic resistance. What's the problem?
So, antibiotic resistance refers to the bacteria changes in response to the antibiotics. So, antibiotics are what we invented to prevent and treat bacterial infections during the World War I. And after that, people can just get antibiotics whenever they want, wherever they want. There's no prescription for it, so people started to misuse and overuse antibiotics, which has caused the problem named antibiotic resistance by bacteria not responding to the antibiotics anymore.
And is there an issue with second generation antibiotics as well?
Yeah, exactly. So after first generation, the second generation of antibiotics was invented as somewhere before 1970s, and after that, from 1979, and 30 years afterwards, there's a new structural category of antibiotics that has been invented. So we have got a really large gap of the lack of antibiotic innovation in our history. So now the third and even the fourth generation of antibiotics invented and put on the market now might not be sufficient enough to catch up the rate that bacteria develop resistance to them.
So obviously anything that drives antibiotic resistance, in other words, makes the problem worse, needs to be identified and investigated. Your research then is focused on non-antibiotic antimicrobials, which are NAAM chemicals, and one particular one, triclosan, which is commonly used, thousands of products, toothpastes, hand wash, that kind of thing. What was your concern about the impact on these chemicals on driving antibiotic resistance?
So my major concern of them is that in terms of developing antibiotic resistance, we know that the misuse of antibiotics and overuse of antibiotics can cause that. So that's why we now make antibiotics prescription medicines so that we can't buy them over the counter anymore. That significantly slow down the misuse and overuse of antibiotics and contributed to slowing down the development of antibiotic resistance. However, those non-antibiotics antimicrobial chemicals, they are still over-the-counter chemicals that we don't need any prescriptions, and they're produced in a huge amount every year. So by referring to the non-antibiotic antimicrobial chemicals, what I mean is those chemicals such as hydrogen peroxide and such as ethanol that we use every day for example, for hand sanitizer, those sort of things. But a majority of them, for example, the hydrogen peroxide, they can degrade after time. And for those, some of them are very persistent organic chemicals, for example, triclosan, which has been found in over 2,000 products. Previously, it's been used in hand wash liquid, and is also a main ingredient in toothpaste. This kind of chemical, they are not prescribed, and you can buy them from any of the stores. That's why they've been discharged into our sewer system in a really large amount. My main concern is that the total amount of those non-antibiotic antimicrobial chemicals may somehow, after one time point, they might contribute to the development of antibiotic resistance more than antibiotics themselves.
Which is a scary thought, right? So you've investigated three ways in which the effects of environmental relevant TCS concentrations might drive antibiotic resistance. Now, this is where the paper gets very detailed and very scientific, but can you describe those three effects that you wanted to investigate?
We know that antibiotic resistance is developed by bacteria as a change of response to the antibiotics. So that development is usually through genetic mutation. That's how bacteria mutated its genetic code. So after that, the previous effective antibiotics might not be able to recognize this bacteria, or the bacteria might express its resistant mechanisms much higher than its like ancestors. So it became resistant to the antibiotics by such as plumping out the antibiotics from the cell or stop the bacterial uptake of those antibiotics. And that's the one major mechanism of how bacteria develop antibiotic resistance. That's through mutation. That's the first mechanism. And after that, this kind of resistance might be encoded by the genetic code of the bacteria. And that genetic code, that encoding for the resistance to the antibiotic, is called antibiotic resistant genes. And what's scary is these antibiotic resistant genes can not only be passed over from the parent generations to the doctoral generations of bacteria, and it can also be shared by bacteria, even across different bacterial species. And that involves the second and the third mechanism of how the antibiotic resistant gene spreads. That's through conjugation, which requires the physical interactions between two adjacent bacterium. And the third mechanism is called transformation. That's when the host bacteria is dead, it releases its antibiotic resistant genes in the surrounding environment, which can be uptaken by the recipient bacteria that haven't got the resistant genes. And after that, the sensitive recipient bacteria can also become resistant to the antibiotics if they successfully uptake the antibiotic resistant genes, which is called transformation. That's the third mechanism.
It's kind of like a horror movie. So basically what you're describing is the ways in which bacteria, as a result of being exposed to this triclosan, might mutate, might conjugate, might transform to develop resistance to antibiotics. And so all these different methodologies you were looking at through the prism of all that toothpaste and hand wash and all the rest of it that we put down into the sewer. So what did you discover?
Yeah, exactly. So basically, in short, is that triclosan can not only induce the emergence of antibiotic resistance, and it can also speed up the spread of this kind of resistance among different sensitive bacteria. So it induces both emergence and the further development of this resistance. And that's how scary triclosan is doing now. And all these can happen under the environmental concentration of triclosan. That's the concentration we can find in our sewer, and we can even find in river water or even in the sea. So as little as like milligram to nanogram per milliliter of the triclosan concentration can effectively speed up this process of the emergence and development of antibiotic resistance.
Listening to that, you'd think, all right, we must immediately stop using toothpaste and washing our hands, but that can't happen.
Yeah.
So what were your conclusions about what should happen and how quickly this problem you've identified needs to be investigated?
So basically, I recommended like two strategies to control this problem. One is we like decrease the amount of triclosan we daily use. We decrease the discharge of triclosan into the sewer. That's to like minimize that's one way to minimize the impact of triclosan to the spread of antibiotic resistance. And the second way is because all these trichosan, they basically mainly discharge to the sewage systems, and those sewage will get together and be treated centralized in the wastewater treatment plants. And if we can remove trichosan by the wastewater treatment processes in the wastewater treatment plants, so after that, the discharge wastewater from the treatment plants will have minimum residue of trichosan. There's also another way to minimize the environmental impact of trichosan. And there are two good news. The first of them is that US FDA has banned the addition of trichosan in hand wash liquid from 2017. But however, that hasn't been promoted to other countries. And the second good news is that Colgate, they promised not to add trichosan into their toothpaste from 2019, last year. So basically, the amount of trichosan that we can find nowadays has been dramatically reduced. That's the good news from my perspective. And I also recommend to do some wastewater treatments to remove trichosan from the wastewater. So our team has been developing a new wastewater treatment technology that can remove those persistent organic chemicals such as trichosan from wastewater. And the removal efficiency can be quite high compared to the previous techniques. Although this is still under development, but I think hopefully in the recent future, this kind of novel technology can be implemented in majority of the wastewater treatment plants. That's another good news I want to share.
And just finally, you also recommend further research. Is that because you've only looked at one strain of bacteria and you'd like to see whether or not there's equally alarming news in other bacteria that might be exposed to triclosan?
Exactly, because I've only done the microbiology experiment on several of the model microorganisms. Although they are included in the very significant high risk categories of bacteria that can develop antibiotic resistance. However, that there's still just limited number of species has been researched. And also, we don't know if there's integrated effect of different bacteria species, and if we have a mixed bacteria community, whether their response to the trichosan might be different. This is unknown because there might be some, for example, trichosan degrading microorganisms, or maybe some microorganisms are more tend to uptake and store trichosan inside their bodies, so the surrounding trichosan concentration might decrease. There might be lots of different possibilities that we need to look deeper into it.
It's such important research. Thank you so much, G, for telling me about it. Dr. G. Lu is a recent PhD graduate from the University of Queensland with a multidisciplinary research background in the fields of nanotechnology, microbiology and environmental engineering. Thank you so much, G.
Thank you, Ellen.